In acetyl-CoA, something that's more relevant to life science in biological molecule, you can do the same thing. So if you have a base here, this will extract the slightly acidic alpha proton of a carbonyl group. CO double bond is a carbonyl group. In this case, we have a ketone. So the first carbon here, that hydrogen is slightly acidic. You have a base here, acid-base reaction, remove the H plus. So you get a C minus left behind. When we have C minus, you have a lone pair of electrons, and now we spotted it. Negative charge lone pair, and the adjacent bond here, pi bond. What can you do? Resonance form. So push the lone pair and push it up. Ta-da! We have another resonance form. And you might ask, which is more stable? Answer is very simple. This is more stable because you compare oxygen negative against carbon negative. Who is more electronegative? Oxygen. So oxygen wants electrons, negative charge better. It can hold it better. So this is of a lower energy than the other one. Okay, the next rule, the slide says, alright, this is a wrong demonstration. So people who are slightly immature, first time doing chemistry here, they think that okay, I'll push it here and stay. But you can't, like I was saying just now, carbon period 2 cannot expand octet. So if I do it and stop here, then this carbon will have 10 electrons in its valence shell. You see 1, 2, 3, 4, 5. 5 times 2 is 10. No good. So this is not a valid resonance form, okay? Learn from mistakes by your friends. So rule number 5, the resonance hybrid is more stable than any individual resonance form. So you have, let's say, two forms. Then people ask you, they look similar, they are the same. Which is more stable? The average is the best because you're putting energy using two different forms and dividing them, so lowering the energy. So it shows you that resonance leads to stability. Lower energy means less reactive, more stable. So to draw it, I've demonstrated to it, so we just go through these slides. Okay, you see from the orbital effect, the alignment of this pi orbital against an empty orbital here, it will just overlap due to the symmetry and right orientation, and electrons are shared. Okay. So this asterisk here on Z could represent a vacant empty orbital, that means there's nothing, or it contains a single electron, that means it's a radical, or it contains a lone pair of electrons. So here, the atom Z I'm pointing to could be a plus charge, negative charge, or no charge with a single dot radical there, and you can still have resonance form between the two the same way. So this is similar to your acetyl-CoA you have seen in previous slides. If I use a base to remove the acidic proton, you have a C minus anion, and this lone pair can go to the left and to the right. Again, you spotted negative lone pair. The next covalent bond here, not the first one, the next one is a pi bond. Bravo, you can do it. So give it a try, push electrons, okay, and here you go. So in all, you have 3 resonance form. 3 resonance form. So even more stable than the acetyl-CoA. Now some practice. Let's draw the resonance form for this anion here. Your carbonate. Very natural ion. Okay, carbonate. Let's draw the 3 forms. Now we're very kind to you. We tell you there are 3. So please draw it. Spotted right. Negative, lone pair, pi bond. You can get it right. Give it a try. Okay, strategy. You can read it. I'll just demonstrate it. It might be easier. Okay. So my strategy is very simple. You take the charge atom and the pi bond, just do a swap. So from here, let's say we're starting at this position, I'll spot, oh, negative, pi bond. So what I do is these two swap. So in the end, I have pi bond and negative charge. Then this guy stay, don't move. And then now the other side, negative pi bond, I change, bond change. Here you go. If you're not asked to do arrow pushing to show mechanism, you don't have to show us how we push it. So this is all that matters. A very fast hack for you to draw different resonance form. Okay, likewise for unpaired electrons and radical, same thing. So I spotted, oh, dot, radical, pi bond adjacent. So what you do? Swap. You see? Swap. And then do it one more time, swap. And that's all. But if you'd like to show how arrow pushing works, please ask me. You have to know that, okay? It is the basis of showing how really electrons move. It's not something that you think, oh, so simple, learning a rule, jump, jump, jump. Okay, no, this is a fast hack. But to show the understanding, you can show how electrons really move using arrow. So thank you for watching. I hope you practice well, learn well, and see you.